You see on this diagram, we've got field lines and equipotentials, and the numbers are the gravitational potential at different distances from the planet Earth in this case. So gravitational potential is the work done to move a 1 kilogram mass from infinity to a point in the field like this. So here it's moving to minus 40 megajoules per kilogram equipotential, and we can calculate that. Okay, you can find that using this equation here, where V is the gravitational potential measured in joules per kilogram. Got minus of the gravitational constant here, which is 6.67 times 10 to the power minus 11. And then capital M here stands for the mass of the planet or star or whatever is in the center there. And R is the distance from the center to a point at which you're trying to find the gravitational potential. Okay, in this example, I'm going to show the gravitational potential on the surface of Earth is around minus 63 megajoules per kilogram. So I'm going to use this equation to calculate it. I've got the gravitational constant here, 6.67 times 10 minus 11, times it by the mass of the Earth, which we can get from our data sheet, so it's given to us, and divide by the radius of Earth in this case, because I'm trying to find the gravitational potential on the surface. So if we do that, and be careful here, there's no squaring of the distance. That's only for gravitational field strength or gravitational force. So here we're trying to find the gravitational potential, which we get roughly 63 megajoules per kilogram minus. Part B of the question, we determine the energy required to move a 1,200 kilogram satellite from the surface of Earth to 6,000 kilometers above the surface. So we just calculated the gravitational potential on the surface, and we want to go to 6,000 kilometers above the surface. So let's say a point like this. Okay, so we're going to have to find the gravitational potential at this point as well in order to figure out the difference in the gravitational potential. So I'm going to use the equation again with the mass of the planet at the top, but instead of radius, I'm going to use the distance from the center of the planet. So that will require that I add the radius to the extra distance, which is 6,000 kilometers, where I've turned that into meters. So gravitational potential at this point is minus 3.22 times 10 to the 7 joules per gram, which is the minus 32 megajoules. Okay, now I'm going to find the difference in the potential between the 2 points that I'm moving between. So if I subtract those two numbers, I get a difference of 30.3 megajoules per kilogram. That's how much energy I have to use per kilogram to move it from the surface to the point 3,000 kilometers above. But I'm going to multiply it by the mass of the satellite because I'm not moving 1 kilogram, I'm moving 1,200 kilograms. And that gives me the total change in the gravitational potential energy. It's gained gravitational potential energy by this much. So basically, if we're moving an object from 2 points, let's say x to y here, or y to x, it doesn't matter. To calculate the gravitational potential energy change, we'll start off by calculating the gravitational potential at each point. We can do that using this equation here, so gm over r1, r2, and then we have to find the difference in the gravitational potential between those 2 points. So that's how much work would have to be done to move it from, let's say, x to y per unit mass. So if we can rearrange this, by the way, we can just take out the g and m in order to make it a bit easier, so you don't have to type it into calculator multiple times. Then once you've got the change in potential, you have to multiply by the mass of the object that you're moving in order to get the change in gravitational potential energy. Okay, so it's tempting to use this as a shortcut, 1 over the distances from the center there, r1, r2 are distance from the center. It's tempting to use 1 over the difference in the distances. However, this would not work. This is wrong, okay, because that's not the same as the expression above. In this question, we're asked to show the escape velocity from the surface of the planet with mass capital M and radius capital R is given by the square root of 2gm over R. We to ignore the effect of any resistive forces, so basically there's no atmosphere around this planet. So we need to give it enough kinetic energy that it goes infinitely far away, R equals infinity, where we've defined the potential as 0. So it needs to be moving fast enough to get there. So first of all, we need to calculate the gravitational potential on the surface where it is currently at. So we can use this equation. And instead of lowercase r, I'm going to use capital R here because I know I'm on the radius of the planet. Okay, so it's going from there all the way to v equals 0. So the change in potential will be the potential on the surface minus 0, which is the gravitational potential on the surface. And now to get the change in gravitational potential energy and to multiply that by the mass. Okay, so that's the gravitational potential energy required to escape the field. And that's going to come from the kinetic energy. So I'm going to make that equal to half mv squared. And as you can see, the m, the small m, which is the mass of the object, is cancelling out. This is important because this means that in our final answer, where if we rearrange it, let's get bring the 2 to the other side and square root it, okay, the escape velocity, like we said, that the question asking for, it doesn't depend on the mass object. So it doesn't matter what the mass object is, the escape velocity is going to be the same if there's no atmosphere. Part B of the question, the escape velocity of a 100 kilogram mass is 15 kilometers per second. State the escape velocity of a 200 kilogram mass. Ignore the effect of any resistive forces. So we just derived the equation for escape velocity. And here the only thing that's changing is the mass of the object that we're firing. And that is not in the equation. So the escape velocity only depends on the radius of the planet and the mass of the planet, not the mass of the object. So the escape velocity will still be 15 kilometers per second for this heavier object.